All right, today we are diving deep into the weather. We're going to look at the invisible battles happening miles above our heads, the very forces that decide if your day is going to be calm and gray or full of dramatic thunderstorms. Have you ever looked up at the sky and wondered that? Why is one day just so dreary and the next is packed with action? It's a great question, right? And it turns out the answer is way simpler than you might think. It really all comes down to a simple vertical tug of war. So to really get this, let's create a main character for our story here. I want you to picture a little bubble, a little balloon of air, just floating near the ground. We're going to call this our air parcel. And its journey, whether it rises or falls, is what dictates absolutely everything. Okay, so our little air parcel needs somewhere to go, right? It needs a path to travel through. Well, that path is the atmosphere itself, and the environmental lapse rate, or ELR, is just a fancy way of saying how the temperature of that surrounding air changes as you go up. Just think of it like the temperature on each floor of a massive skyscraper. But here's the thing, our air parcel has its own set of rules for temperature. As it rises, it expands and gets colder, and if it sinks, it gets squeezed and warms up. We call this its adiabatic rate. So now you've got two different things going on, the temperature of the environment and the temperature of our parcel. And this, right here, is where the battle really begins. Okay, if you remember just one thing from all of this, let it be this. It's just simple physics. If our little air parcel is warmer than the air around it, it's less dense, so it's going to rise, just like a hot air balloon. And if it's cooler, it's denser, so it's going to sink. That's it. That's the one rule. Every single weather pattern we're about to talk about comes right back to this simple fact. All right, let's jump into our first scenario, absolute stability. I like to think of this one as the heavy balloon, and, well, you're about to see why. This thing just does not want to go up. So, in a stable atmosphere, our little air parcel will always be colder and because of that, heavier than the air around it. It has no natural lift. Even if something like a mountain forces it upwards, the second that push is gone, it just sinks right back down to where it started. And hey, the numbers right here tell the whole story. Just look at the 1,000-meter line. The environment around it is 15 degrees, but our parcel has cooled all the way down to 10. It's colder, so it sinks. And if you push it even higher, that temperature gap gets even wider, making it want to fall back down even faster. So what does this actually look like for us down here? Well, this is your classic gray, dreary, overcast day. The air is fighting against any vertical movement, so any clouds that do form just get smeared out sideways, like a big flat blanket. You get those gray stratus clouds, maybe some light drizzle, but nothing exciting. Now, if you want to know the most extreme version of this, it's something called a temperature inversion. And this is where things get really weird. It's a layer in the atmosphere where the temperature actually gets warmer as you go up, which is the complete opposite of what normally happens. And an inversion has some major real-world effects. It acts like putting a giant invisible lid on the atmosphere. It traps everything underneath it. That's why you get those really hazy, polluted days in big cities. It can also trap moisture near the ground, which leads to widespread fog. There's just nowhere for anything to go. Okay, so we've seen the calm, heavy balloon. Now let's flip the script completely and talk about scenario 2, absolute instability. Meet the eager balloon. Once this one starts rising, there is no stopping it. In this situation, the atmosphere is just primed for things to go vertical, and fast. Our air parcel starts its journey, and at every single level, it looks around and finds that it's warmer and lighter than its surroundings. So it just keeps going, accelerating upward all on its own. And once again, just look at the numbers. Imagine a super hot, sunny day, right? The ground is just baking. This makes the air cool off really fast as you go up. Look there at 2,000 meters, our parcel is a full 5 degrees warmer than the air around it. It's like a rocket at this point, creating these powerful updrafts. So what kind of weather do you get from this? Yup, the big stuff. All that air rushing upwards builds those huge, towering, puffy cumulonimbus clouds. These are the engines of our weather, the clouds that give us strong updrafts, heavy rain, and thunderstorms. When you see a sky full of these tall clouds, you know the atmosphere is unstable. Okay, on to our third and final scenario. And this one is actually the one we see most often around the globe. It's called conditional instability, or my personal favorite, the reluctant balloon. It has all the potential for drama, but it needs a little nudge to get started. So here's the big puzzle. In this scenario, our air parcel actually starts out stable. It's cooler, it's heavier, it wants to sink. So how in the world does this situation end up creating some of the biggest storms on the planet? Well, it all comes down to a special condition. Okay, let's walk through this step by step. First, that reluctant air needs a little push, maybe from a mountain range or weather front. As it's forced up, it cools down. Eventually, it gets cold enough to form a cloud. Now, step 3 is the magic moment. When that water vapor turns into tiny cloud droplets, a huge amount of energy called latent heat gets released. This heat warms up our little parcel from the inside, and bam, it suddenly finds itself warmer than its surroundings and it takes off. This table here shows you that exact tipping point. See? At 1,000 meters, it's stable, it's cooler, and it wants to sink. But once it gets that push and that latent heat kicks in, look what happens at 4,000 meters. The environment is at freezing, but our parcel is now a cozy 5 degrees. It has crossed the tipping point. It's now unstable, and it's off to the races to build a powerful storm. Okay, so we've gone through the 3 big scenarios. Let's pull it all together now. How can you actually use this knowledge to read the sky and have a pretty good idea of what's coming? Think of this as your ultimate cheat sheet. It's super simple. If the air is stable, the parcel's always cooler, you get flat stratus clouds, and it's probably overcast. If it's unstable, the parcel's always warmer, and you get those puffy cumulus clouds that can lead to thunderstorms. And if it's conditional, well, it needs that push, so it could be a nice day or it could turn stormy. So seriously, the next time you step outside, just look up. The sky is telling you one of these 2 stories. Are the clouds all flat and spread out like a boring gray sheet? That's a story of stability. Or are they tall and puffy and look like they're growing upwards? That is a clear story of instability and some powerful forces at work. So when you boil it all down, here's what you need to remember. The entire story of our daily weather, from a light drizzle to a massive thunderstorm, is just a temperature battle. It's all about whether that little rising parcel of air is warmer or cooler than the world it's moving through. And now, you know how to read that story. So tomorrow, I want you to look outside, but don't just see clouds, see the physics behind them. And ask yourself, what story is the atmosphere telling me today? Is it a story of stability, or is it a story of chaos?